Guys, you ever been in the woods, foraging, looking for mushrooms, walking along, and just as you lean in, you see something vivid, bright blue, and you're like, oh my goodness, what could be causing such a bright blue color out in the middle of the woods? Well, that color that you see as you lean in is known as you lean. You know, I gotta throw in a dad joke. Hey guys, it's Mr. Jeff. Welcome back to the channel. And today we're gonna talk about colors in mushrooms, especially pertaining to how some mushrooms can actually change colors. So let's explore this idea, guys. I think we're taking it back to middle school with this one, guys. Remember the color wheel? Remember the electromagnetic spectrum? Well, I just want to explore some of these underlying concepts before we dive into the mushroom side of colors, just to give us a refresher so we know what we're talking about. So as you may recall from back in the day, all light, both visible and invisible forms of light, is merely photons traveling in these electromagnetic waves, right? So I'm just drawing just a rough diagram so you guys can kind of get an idea here. But these electromagnetic waves can vary in their frequency or how often they oscillate in any period of time. And that oscillation, the up and downness of these waves is what we refer to as frequency. And as you can see, over the course of a period of time, longer waves oscillate less frequent than shorter waves, which are going very fast in their oscillation, even though the wave itself is traveling at the speed of light. So what's happening here, and I want to use, this is a rough analogy. This is probably not the most accurate way of explaining this, but it's a great way of understanding a concept here of how energy increases as we shorten our wavelength and increase the frequency of the waves. We also see an increase in energy. So I drew up an air hockey table, and here's a little fun fact. Did you guys know this little thing is called a mallet? I did not know that until I was researching this video, but that's pretty cool. But if you take your mallet on an air hockey table and you hit the puck with the purpose of trying to get it to just bounce one time across this distance into the goal, you're creating sort of like an oscillation or a wave, right? But creating that longer distance wave, and let's say it takes 1 second to get across. We're going to cover this distance in 1 second. That one wave doesn't take much energy or much power on my end to hit that puck to bounce from here to there in 1 second. However, if I'm trying to span this same distance in 1 second while creating a higher frequency wave where I'm going to bounce my puck back and forth, back and forth, back and forth, let's say 100 times just to get it to the other side, how much force or how much power am I going to have to put behind that puck to get it to get to the other side in 1 second, yet creating high frequency in the oscillation? It's going to require a whole lot more power. So just as we have the analogy there with the air hockey table, imagine, if you will, more energy required to be able to get this speed of light electromagnetic wave to oscillate at such a high frequency. Now, what does that all have to do with all this colors and all this stuff? Well, we're almost there, guys. Keep with me. Stay with me here. So, on the long wavelength, less frequency, longer distance waves are going to be your radio waves. That's the reason why a radio wave can travel miles and miles, transmitting electromagnetic radiation over great distances, which we can then interpret and tune to a station on a radio and listen to music from miles and miles away, right? But as those wavelengths get shorter, it takes more energy and these waves get more powerful, but their power is over a shorter distance. So we shorten the gap. we start hitting microwave range. And it keeps going further. We're hitting into infrared, and this is about where 5G radiation falls. When we think of like my cell phone, 5G towers, we're about in this vicinity. We keep moving over with greater energy, shorter wavelength, higher frequency into visible light, and that's where we're going to be spending the majority of this video. But let's go past this a little bit into ultraviolet, and then as the intensity of the energy increases here, and maybe intensity is not the right word, but as we get more powerful in our energy, we get more frequent waves, but they're shorter distance, so they can't really affect long distance, but what they do in the short distance is very powerful. Well, now we're dealing with X-rays, and we end with gamma rays, which both X-rays and gamma rays are going to be ionizing, including even ultraviolet. You're getting into a range where these waves are so powerful that they're able to knock off electrons off of the atoms that they occupy, ionizing the atoms. And that's the danger in this end. This is how it's danger to life, how ultraviolet rays cause DNA damage, and then we get into X-rays, which causes more, that can cause cancers, and gamma rays can literally just kill you dang near instantly. I can only imagine as you approach infinity in the frequency, how much energy it would take. But in theory, if you had an indisposable amount of energy, you could create some rays that could literally just destroy everything, turning everything into plasma. But that's more hypothetical, theoretical. But anyway, just trying to show you how as energy increases, we get more frequency, but we get a shorter distance wave. Now, visible light that we can perceive with our eyes is going to fall in a wavelength that's super tiny. I'm talking between around 400 nanometers to 800 nanometers. That's the distance of the actual wave that we're referring to. Nanometers are super tiny. So tiny that they can actually fit inside molecules. Within the width of a molecule, some of these wavelengths can hit. So let's bring it over here to my little color wheel that I was demonstrating here. So starting at the 400 nanometers, that wavelength to our eyes is going to appear as violet. And I know my markers, my chalk markers, don't bring out the best coloration of this, but you can kind of get the gist of it here. But as that wavelength goes further, or longer distance wavelength, we eventually end up to red. And if we kept going, we enter the infrared. And if we were to go smaller, we enter ultraviolet, right? All right, guys. So here come the molecules. So one thing I didn't explain to you guys already is this concept in chemistry known as conjugation and resonance. We talk about molecules having resonance when electrons are being shared by different atoms within the molecule. The electrons are able to, well, let's bring it over here. Let me explain this further. So I use this one as an example, this molecule azulene, which derivatives of this azulene are found in mushrooms such as Lactarius indigo, which gives it its deep, vivid blue color. I can also show you some of these other molecules, and we'll notice a trend. I kind of want you guys to see something, see if this catches your eyes. We'll call this a little pre-quiz trivia, or pre-trivia quiz rather. Let you guys take a little quick quiz here. And do you notice something about all these molecules? Some of them are long, stretched out, skinny. Some of them look more complex. Some of them are cyclical. But there's a trend I notice in a lot of these different molecules and moieties. All right, if you haven't figured it out yet, let me show you guys. So what I notice here is you have a double bond followed by a single, followed by a double, followed by a single, followed by a double. And this alternating single and double carbon bonds here that we have, whether it's cyclical in these rings or whether it's in succession in these chains, you see it here as well. Double bond single, double bond single, double bond single, double bond single. what this is allowing electrons to do is they can actually travel along the course of this. They call it conjugation. And sometimes the conjugation leads to resonances, such as you find in benzene rings and phenols and stuff, like we see in here and in here. Sometimes they're represented, instead of drawing the three little sticks to form the three doubles, they'll just put a little circle inside. All I'm trying to explain to you here is this concept known as conjugation, where you have the alternate single and double bonds. It allows electrons to travel amongst each other in different atoms in the molecule. And for whatever reason, the laws of physics allow certain bandwidths of light fit along this track, if you will, we might refer to it as. So here, let me back it up a little bit. So beta carotene and lycopene, you may have heard of these molecules. They're not necessarily ones you think of in fungal kingdom, although these can be found in certain fungi. But the reason I bring them up is because they're found in nature as a whole, and they are colorful to our eyes. We perceive a color all because of photons coming at a certain bandwidth. So we've got, like right now, I've got sunlight shining down on my truck. Imagine the sunlight, those photons coming in, those electromagnetic waves are coming in all sorts. Let's bring it back to the other side of my truck real quick. My sunlight that's shining down on me now is actually coming in all these. Now, some of them are not reaching me because of interacting with particles in the atmosphere, so they don't quite make it to me. But some of the light does make it to me as infrared light, because right now I feel the warmth hitting my skin. That's the infrared bandwidth hitting me right now. I also have visible light hitting me. The fact that I can see my skin color, it has a tone, is because of the visible light hitting my eyes, bouncing off my skin. Ultraviolet is hitting my skin. That's the reason I get a tan, is because of chemical processes that are interacting with those ultraviolet bandwidths. There's even X-rays and gamma rays leaving the sun, traveling to us, but whether they make it to me or not is another question, because we have things between us and the sun that block a lot of this. Besides the fact that it's very easy for some of those smaller bandwidths to interact with particles. They have a hard time traveling long distances, right? But anyway, all right, so back over here, we got the full spectrum of all these electromagnetic waves coming as photons hitting a beta carotene molecule, which beta carotene gives carrots their orange color. Well, the reason it gives orange color is because out of all those bandwidths that are coming through, a certain bandwidth gets absorbed in this span of this conjugation here. Remember the alternate double bond, single bonds? Well, there's a distance you can literally measure in nanometers. And the measurement of that distance is the same distance of the oscillation of a certain bandwidth color. Take a guess as to what color matches with this. And this may sound counterintuitive at first, because I'll tell you what, it's not orange. It's not yellow. It's not red. Take a wild guess. All right, so what happens is you only see colors that are reflected back to you, but colors that are absorbed, you don't see those. So you're seeing kind of the opposite. And the reason I made this in a circle, even though it starts here and ends here, is because with this color wheel, if you're seeing the color orange, it's because the opposite color is being absorbed by the molecule that is orange. And in the case of beta carotene, it absorbs in the blue color. It absorbs in this nanometer range in here, allowing us to only see over here. Okay, back over to this side of my truck. Let's look at the molecule lycopene. Now, lycopene's conjugation chain is a little bit longer than beta carotene's. We could actually count it out. So if I count double, 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 that's 3, 4, 5, 6, 7, 8, 9. I see 9 in a row right there. But when you look at lycopene, it has the double bond starting here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That extra length, just the extra length measured in nanometers makes the difference on the color of lycopene versus beta carotene. Take a wild guess. If you're familiar with lycopene, lycopene is found in tomatoes and certain fungi too. But you know the color is the color of tomato. So what color might it be absorbing that's allowing us to see red? Go over to the color wheel. All right, so if we're seeing red in lycopene, that means that that molecule is absorbing over here in this bandwidth. And remember, beta carotene was over here. It was in the 400 and some odd nanometers absorbing blue. Well, lycopene's a little bit longer. The nanometers are over here closer to 500 and some odd nanometers. That slight difference in length absorbs green, allowing us to see red. Man, isn't nature wild? Quickly, while we're still talking about nanometers and color absorptions, I have up here porphine, which is sort of the foundation behind multiple natural molecules such as chlorophyll, hemoglobin, myoglobin, and vitamin B12. The only difference is some little bit differences on the outside, different moieties attached, but primarily a metal ion that sits right in the middle is going to determine, in many cases, what the color of this porphine is going to end up looking like to our eyes. Because here's the crazy thing, colors really don't exist. Colors are an interpretation or a fabrication of our brains or what we determine. So there's really no such thing as green, blue, orange, yellow, red, or purple, or all these colors outside of the way we interpret the world around us. That being said, if we put a magnesium in here in this porphine, if it has a magnesium center, it's going to absorb, I believe it would be absorbing in the, what would it be, the reds, because it gives a green color. Chlorophyll is going to be green. Hemoglobin, which is red to our eyesight, would be absorbing the opposite on that color wheel, and so does myoglobin. Myoglobin gives muscle tissue its red color. Vitamin B12 is also a nice darker, vivid red color, and it's due to a cobalt. Oh, I didn't mention hemoglobin has an iron. But these different metal ions can determine different color variations of these porphines. And let's jump down to this molecule. This one, being a flavonoid, is not actually found in any mushrooms that we know of, but delphinidin is cool because it gives hydrangeas its variable color, all because of aluminum in soil. If aluminum interacts with delphinidin, it can actually change the molecule, allowing it to resonate at a different color frequency to our eyes. So in acidic conditions, if I'm not mistaken, isn't it pink? And as the soil gets more basic, it turns more blue. I believe that's the case with hydrangeas, but it's due to this molecule interacting with aluminum under acidic conditions that allows these color change. So, and once again, we've got these conjugations going on in these atoms, the alternations between the doubles and singles, which allow for the absorption of a narrow bandwidth. Just that bandwidth changes as the conjugation length shifts. Actually, I believe in the case of delphinidin, these molecules are planar, meaning they're like flat, two-dimensional, and they can be stacked on top of each other molecularly like sheets. And that stacking, due to removal of some of these hydroxyl groups or modifications, allow for the stacking, allows it to go planar, and that's the color change. But that's another deep topic for another day. Let's keep going with this, but back to the mushrooms, right? So on my truck, I have 3 out of many compounds found in the fungal kingdom that give us colors that we can perceive. The ones I wrote up here in particular, we have variegatic acid. This is one of many derivatives from a compound known as atromentin. Atromentin is found in many boletes, I believe it's a yellowish orange color. But as it is processed through different enzymatic reactions, including oxidation, like when you cut some of these mushrooms open, other compounds are formed. And the different compounds that are formed, they have that conjugation. Let's follow it again. Let's look at some of these double to single. Like if I went here, double, single, double, single, double, single, double, single, double, single, double, single, double. So you can see how an electron can be shared amongst this conjugation pathway. And remember, the distance of the conjugation can determine the coloration of these molecules. So these different formulations, and I'm only using variegatic acid in this case, found in boletes, but these compounds will change color just based on the length of these conjugations. And that's why it's so simple. It's almost magical to us to see a mushroom that's yellow and red, vivid yellow and vivid red, and you take a knife to it and you cut it in half and it instantly starts turning blue. Or maybe it takes a minute or two for the blue to come through, but that's just because of the different enzymatic reactions. Some of them are very fast, some do take a little bit longer, but you get different compounds. I mentioned variegatic acid. You also got xericomic acid, isoxericomic acid, and a handful of other of these, can I call them quinoids? These are compounds that contain like a quinone group. Here's a quinone, basically like this ring structure with the ketone coming off the side. I'm not the huge expert on some of these compounds. That's why I want to call them quinoids, because they may not be exactly quinones. Quinone methides particularly are going to be blue. They're going to give us a blue coloration in our perception, whereas like a terphenyl quinone is going to be red to brown in color. Grevelins, orange to red. These are found in, I believe, exclusively in Pseuilus species. They're actually used as a chemo biomarker for identification of Pseuilus species. Polyketides can come in various colors. Carotenoids, I already mentioned beta-carotene and lycopene, which can be found in certain fungal species. They're going to be red, orange, yellow. Quinone methides, I think I just mentioned that, is going to be blue. Your azulene derivatives are going to be quinone methides. This silosyl oligomer, I can't even say the word. Oligomer, there we go. Silosyl oligomers. An oligomer is a little bit smaller than a full polymer. But in this case, it's just two silosins. One is inverted and attached. And instead of having the hydroxyl, it has the ketone here and here. But you can see the dimethyl tryptamine formation right here with that ketone attachment. Inverted, doubled, by themselves, a single tryptamine like psilocybe or psilocybin will have no color perception to us, because remember, the visible light, what we call visible light, is just a certain bandwidth that's hitting our chromophores. By the way, a chromophore is a color-producing portion of a molecule, and it takes one to know one. So we have chromophores that resonate at the same frequency as some of these chromophores do. So what's happening is, remember, the absorption of certain colors is going to only allow certain to reflect to our eyes, and the ones that hit the cones in our eyes, or the color receptors in our eyes, are going to only match up with the ones that match the molecules. And in this case, we get the perception of blue when psilocin is polymerized and forms these larger conjugated molecules. Remember, it's the conjugation that gives it the color, and if it's too short of a distance, it misses the whole bandwidth that we can perceive. The distance of the conjugation has to fall between 400 and 800 nanometers for us to perceive it. And if it's over here, if it's absorbing in this range, we're perceiving this. If it's absorbing over here, we're perceiving over here. So in the case of like your callosal oligomers, we are perceiving a vivid, rich blue. So it's absorbing over in here, which means that that conjugation spot on the molecule has a distance that's going to be between 620 and 580 nanometers. Get you a ruler and go measure it. Prove me wrong. Hey, if this is the kind of deep dive fungal science that you're into and you haven't subscribed to my channel yet, what are you waiting for? I try to bring these videos on a regular basis. I'm doing this every Monday night. And if you stay after the video with me here on the live premieres every Monday, you get to chat with me live. We get to discuss this further if you'd like. We can explore further topics also for future video ideas. Hey, it's Mr. Jeff. Thanks for being on the channel. Like this video, please. Help the algorithm out. And until next time, peace. So what's the difference between yellow and blue? About 100 nanometers.